Recording. Okay, so what is going to happen today? So last time I started the discussion with the famous Paris Harrington theorem. Now, why is it famous? Because it was considered to be the first example of a purely combinatorial statement which is so complex that it cannot be proved from the piano axioms. Now, last time we have seen how they compare to the fast-growing Heidi functions, and that the fast-growing Heidi functions are not provably total in piano arithmetic is part of the lecture proof theory. So in this lecture, we just see that the Ramsey functions are growing rather quickly. Now, today, we will see how to obtain a phase transition for this. And that's delicate in the sense, as I already said, it was almost impossible to improve the existing proof. And but at some moment I was able to do so. Now let us recall the basic definitions. So juvenile is also in for the first time. So I will not recall the full proof, but how was the proof organized? We had first a shift coloring. And we had three colors. 0, 1, 3. And now we were considering, so we assume that these are, let's say, decreasing. So not that much. But now we compare beta 1 and beta 2. And if there are difference in the Cantor normal form, they will first place where beta 1 is different from beta 2, I cement. And if this is going to happen, if we compare beta 0 with beta 1, there's a component in beta 0 where the comparison happens. In that comparison, the index is bigger than the corresponding coefficient in comparison of beta 1 and beta 2. Then if d beta 0, beta 1 is less than or equal to d beta 1 and beta 2, then we look at the coefficients in the comparison of beta 1 and beta 2 and beta 0 and beta 1. So we have the component. So alpha is normally written as omega to the alpha 1 m1 plus as omega alpha n mn. And if I have here omega alpha I m I, this is position I, where the d function refers to, and the coefficients function k beta 1 beta 2 is the coefficient at the position where beta 1 and beta 2 are different. So we go into the ith position given by the distance function, and then we collect these coefficients. And if this one is smaller than k beta 0 beta 1, that's this color. And finally, that's the otherwise case. Now, what was the role of this? The role of this was verified that if I have a sequence of ordinals, let's say decreasing, m is big as 2. Now, what's the point? We want to get information about how long the sequence M can be in terms of information on the first component. Now, in general, we cannot say anything, but assume that the sequence comes from a sort of homogeneous set for this shift graph coloring. So assume that E beta I plus 1 beta I plus 2 is always the same color C for some C one of these colors over here. And all I less than equal to m minus 2. Then we have three cases depending on the colors. First one is if the color is 0, then we see that the distances are going to the left. And in that case, we can conclude with corresponding exponents in pantanomal forms are now strictly increasing. This one I showed last time. Second, if C is 1, then you get a descending sequence of words. And then we get a descending sequence of natural numbers. So then M is bound by the maximal coefficient of beta 0. So what was the maximal coefficient? The maximal coefficient of alpha is the maximum taken over M1 to Mn, and the maximal coefficients of the exponents. The third one, if the color is 2, then we do not get an increasing sequence, but we get a decreasing sequence. And this one I proved last time. But we see when we have homogeneity for the shift graph coloring, either we get that the length of such a sequence is bounded by the complexity of the first term, or we move a decreasing sequence into an increasing sequence of exponents, or into a decreasing sequence of exponents. And so somehow we move the question of how long this sequence is into a question of how long the sequence of exponents becomes. Now, the shift graph coloring is used to define another coloring, the master coloring, which we need for the Paris Harrington proof. What was this? Well, I will just call it definition. So we have Ks. It's a function going from x plus 1 elements, sets with s plus 1 many elements, and they are all smaller than omega s k plus 1. And this one is an omega tower, omega times s, and on top I have k plus 1. And I go into finite set CKS. CKS is basically an exponential function, so it's an exponential number. So the recursion was CK1, it's just given by the numbers from 0 to 10. And CK f plus 1 is, I take the previous set union, and then I have an S tuple with 3 elements of this one. Now, EKS is defined by recursion on S. If omega k plus 1 is bigger than alpha, the form omega to k times m0 plus omega 0 times mk, alpha bigger than beta, which is from omega to k times m0 1 omega 0 times k time. So if alpha and beta are smaller than this number, I can write alpha and beta uniquely in this form. So it could be that M0 is 0, but this is not necessarily a Canton normal form. But since we are dealing with these small ordinals, you can just write this as polynomials. And then T, K1 alpha beta is the first place. If alpha is bigger than beta, there will be a position I, where position I, the coefficient in alpha is bigger than the coefficient in beta. So it's at least I, such that mi prime is smaller than m. And now, since we do induction on S, now consider the situation omega S plus 1 bigger than beta 0, bigger than beta S plus 1. Delta I will be what? Well, when I compare ordinals of this form, let's say if I have beta I and beta I plus 1, then beta I is bigger than beta I plus 1. So there will be a position in the Canton normal form of beta I, where the summand is bigger than the corresponding summand in beta I plus 1. And the summand has a form omega to something times coefficient. Then I take here the corresponding exponent. And Ci will become the value of the shift graph coloring, which is just 0, 1, or 2, with these small heads on it to make them different from the natural number. So the reason why I chosen here these heads is just to make them different from the colors from 0 to k, just a formality. Otherwise, there's nothing behind this. Okay. Now the magic starts.
Excuse me.
Yeah, question.
Could you please also show the complete right board?
Yes, I can do so. Now better?
Yes, thank you.
Yeah, well, it's good that you say this because I was not aware of the problem. So
yeah, maybe also a little bit to the left because now I don't see the left board.
Yeah, that's fine. Better by now?
Yeah, this is good. Thank you.
I see. Very, very good. So anyway, now comes what is very funny. So Ek S plus 1, beta 0, beta S plus 1 is what? And if C0 is equal to C1 is equal to C S minus 1, 2. And then what? Then I have the case over here. When I have a decreasing sequence of exponent. And the decreasing sequence of exponent is one shorter. Here I have a length S plus 2. Now I have here the sequence delta 0, delta S. Now the beta i's are smaller than both. I have to define it by recursion on S. So I assume that beta i's are smaller than omega S plus 1, k plus 1. And then the delta i's are the exponents. The delta i's, delta 0, smaller than omega S of k plus 1. So this means this decreasing sequence of ordinals is the sequence to which I can apply the previously defined function tks. Now, the next case is C0 is equal to C1 equal to CS minus 1 equal to 0. If I'm in the case of 0, I move the decreasing sequence into an increasing sequence. Now, if I reverse the order here, I get a decreasing sequence. We have delta S, delta 0, and here comes CKS. And if those two cases don't hold, then this is a situation of chaos. Then I take the tuple, this one here, C0 to CS minus 1, tuple of length S. And then I'm in a situation where I'm here. No, I'm here, right? So I have to move TKS plus 1 into the set. Either I get an S tuple, I get the S tuple here, or I get a shorter tuple by applying the TKS function. So this function is pure magic, and it's well defined by using this lemma over the shift graph function. So I will not reprove this one. Now, what is new compared with the old proof? So my contribution was basically coming up with this new clause in the definition of the master coloring. Now, what's the point here? Well, lemma. Assume certain things. They want to S and K, S smaller than N, KS. And assume that you have a decreasing sequence of ordinals smaller than omega SK plus 1. Now comes it. If at this moment you cannot say much about M in complexity of beta 0, but now if the sequence is a homogeneous sequence, if TKS of beta I up to beta I plus S, if this always gets the same color C in this set of colors for all I which are involved, then M is bounded by the maximum coefficient of beta 0 plus the height of beta 0, where the height in ordinal alpha is the least M such that alpha is one of them. So it's a very tricky statement. So we want, what is the goal in total? We want to show that we want finally to define a partition which is bad in the sense that all homogeneous sets are short. Now what we do here is we define a partition on ordinals such that certain homogeneous sets are short. So if you have a homogeneous set, then if it's descending sequence of ordinals, then the canality is basically bounded by the complexity of the first term. The maximum coefficient is a natural number showing up in beta 0, and then comes here the height of beta 0. And that's pure magic, but the whole proof is pure magic. So, and what we did last time, last time, in this first version, I had here the rank of beta 0. What was the rank of beta 0? Was the rank omega to the alpha 1 times n1 plus omega alpha n times n was the maximum taken over m1 to mn, the rank of alpha 1, rank of alpha n. And then comes the innocent addition of the n over here. And for the old Ramsey partition, one could prove the same lemma by replacing here the maximum coefficient by the rank function. But for the phase transition, this estimate is not good enough. Therefore, I have to squeeze it even sharper down to get rid of this n. Now, where the n is needed, or where the deletion of the n is needed, a different question. It will be seen at a certain moment, which I try to highlight. Now we do the proof, and I will basically recall the whole proof. Otherwise, you just do straight, right? So we do this by induction on S. So S equal to 1. So what is going to happen? Then we have this simple coloring. So beta I as follows: it's omega to the k times n by 0 plus omega to the 0 times n I k. And now we have what? The He function is giving constant value C. So we zoom in at a fixed position in all these occurrences. So here's a fixed position I. So then we have that n color chosen. NC0 is bigger than n to n. And since in this case we have a descending sequence of natural numbers, we can conclude n is bounded by NC0. NC0 is a coefficient in beta 0, so bounded by the maximal coefficient. And beta 0 smaller than the maximum coefficient of beta 0 plus the height. Okay. That was the case S equal to 1. Now we do the induction step. So assume certain side conditions. Come to S plus 1 to n. C is our color, which is constant. We have a descending sequence of elements. And we have homogeneity. E, K, S plus M, beta I plus 1. Obviously, it is the same color. For all I M, S, and M. Okay, what cases do we have? Well, we have here this coloring T. Either we get a tuple of length M, or we get shorter tuples. Because if we are moving from S plus 1 into S, and we see here the tuples showing up here are shorter than this S. So assume that we have an S tuple, meaning that we are in this case. The otherwise case. one is C is an S2. CI is as before. It's beta I, beta I plus 1, beta I plus 2. For I is minus 3. Then what? Then for I representing M minus S minus 2, we have what? We consider T K S plus 1, beta I plus S plus 1. Now this is the same as EKS plus 1. Here I start with beta I plus n. And I go until to beta I plus x plus 2. That's this property. Now what? Now the value C is always the same. We have always this value. So we have here Ci I plus x minus 1. That's the value of this coloring. And here we have the I plus 1, I plus 1. And now comes this magical argument. E0 is equal to C1. So I is equal to 0, right? So C0 is equal to C1. And then C1 is equal to C2, etc. So we have a domino effect. Hence what? I is equal to I plus S, or M minus S minus 2. What does it mean? This means in total that C0 is equal to M minus 2. So all the C's are the same, so that we can apply now information on the shift graph coloring. So could it be that the CIs are all 0? The answer is no, because then I have applied this coloring. This coloring assigns not a tuple of length S, but a shorter tuple. So the color cannot be 0. And for the same reason, the color cannot be 2, because if the CIs are all equal to 2, I have to assign this coloring, which is shorter. If they're all the same, and if you have an S tuple, then the conclusion is that C0 is in color 0. And what? No, it's not color 0. If it's color 0, it's too short. If it's color 2, is too short, so the color is 1. Okay. Color is 1. And what are the CIs? The CIs are the values of the shift graph coloring. And if the values of the shift graph coloring are always the same, and the color is 1, then the length of this sequence is bounded by the maximal coefficient. So follows that M is bounded by the maximal coefficient of beta 0, which is strictly smaller than the maximal coefficient of beta 0 Yes, the height. And those, nice. Now the other cases come by induction hypothesis. This was case one. It was in this case here. That's fine. Now let's look what's going to happen here. And then I shift basically the claim into assumption on the exponents, applying the induction hypothesis. And since the exponents are living in a world 1 omega power smaller, everything is fine. Now I have to do the argument. Yeah. So case 2. Case 2 is its color is in CKS. And now let delta I be the exponents. I less than equal to m minus. Okay, now okay, so we have. Let's first look at this case and then we look at this case. Case 2.1. All these colors are equal to 2. So you did not miss much because I basically recalled large parts of the proof from last year. So what I'm going to show is this one, namely if we have decreasing sequence of ordinals which are homogeneous for our master coloring, then this sequence is short. And I covered the case, and the color was this one. Now I'm covering the other cases. So the case 2 was C is the shorter ripple, and 2.1 is the shift graph coloring obtains value 2. What then? We have what? Color is 2. Then the exponents are decreasing. So omega S k plus 1 bigger than delta 0, bigger than delta m minus 1. Somehow important, the length of the sequence in the exponents is 1 shorter. Because they're coming from the comparison. Anyway, for I less than equal to minus 1 minus S, we have what? C is K S plus 1. Eta I plus S plus 1. And this is the same as EKS. Delta I plus S. So we see the exponents for sort of homogeneous set for the shorter master cloud. Now, since we have here homogeneity, sort of homogeneity, induction hypothesis gives what? M minus 1 is bounded by the maximal coefficient of delta 0 plus the height. Now this means M is smaller, the induction hypothesis is strict smaller. I add a 1 over here. So what? Here's delta 0, of course. Now the height of delta 0 is 1 smaller than the height of beta 0. So the maximum coefficient of beta 0, delta 0 is an exponent in beta 0, so the maximum coefficient of beta 0 is bounding this one. And the height of beta 0 is 1 bigger than the height of delta 0, so I get what I need. That's fine. And the last one, just following case. Namely, with E0 is m minus 2 is color 0. Then we have color 0. So from a decreasing sequence of coordinates, we get an increasing sequence. Then it follows that delta 0 is smaller than delta m minus 1. Now the color C is TKS of beta I plus f1. And now we take TKS in this is plus 1. TKS in reverse order. Delta I plus S. Delta I. For I n minus n minus S. Yeah, but it doesn't matter that much, right? When you read all these equalities in the right order, namely not from 0 to m minus 1, but backwards from m minus 1 to 0, then you get a situation where you can apply an induction hypothesis. So the induction hypothesis implies m minus 1 is bounded by maximum coefficient of delta a minus 1 plus height of delta. But wait a minute, here's a problem, because what is the problem? Delta m minus 1, but we need here beta 0. So we are lost, we can give up, right? No, we cannot give up, because last time we have this strange lemma. In the comparisons of the contonormal forms, we went to the left. The information about beta 0, delta m minus 1 is contained in the beta 0. It was a strange comparison with contonormal forms. So it seems somewhat to be impossible, but delta m minus 1 is an exponent in beta 0. And it's somewhere to the left. And the reason is that these exponents based in contonormal forms, they always went to the left. So this means so we have this lemma basically here's the first exponent, down. Here's the delta n minus 1. But the exponents in beta 0, the property that well, the delta m minus 1 is an exponent showing up to the left of the position over here. So this delta m minus 1 is still part of the original contonormal form of beta 0. And therefore, we can bound this by maximum coefficient of beta 0 of the height of beta 0. Because delta m minus 1 is an exponent in beta 0. So that is sort of magic. But now this is not Cantor, this is not Paris Harrington, this is just a lemma about properties of our shift graph coloring. Now we have to squeeze out information about Ramsey functions. So what's needed is this lemma. So let us recall what was Paris Harrington. Paris Harrington was basically saying following statement: for all dimensions V, for all colors C, for all numbers M, there is the Ramsey number R so big such that for all positions P from the B subsets of R into C, there exists an intercept H and in the B subset of R, such that P, when restricted to the B subsets of H, and get constant value, and the cannulity of H is as big as the maximum taken over M, so that's the number M here, and the minimum of H. Now we want to show what? That this R grows astronomically, bigger than the Ackermann function. And we show that this R is large by using this master column. But that I already did last time. What we now consider as Paris Harrington with respect to parameter function f. Then we do here f of the minimum of h. And then the question is, for which functions f do we still get large growth? And basically, the rule of thumb is basically A does not prove H for fixed iterate of log function, and A does prove H for the inverse of the power function. That's our plan. Now we don't do proof theory, so we try to find out that if you are in the situation that this function f is a fixed iterate of a log function, then we get enormous speed. And that's now the part of the following. So let's say EH BCF of M is the least R, such as for all P from the subset of R. H is homogeneous, and cannulity of H. Cannulity of H is at least as big as maximum taken over M of F of minimum of H. Now what we are going to show is the following theorem. A. Let S be a number. Let D be fixed. D will be this number. Now, this number S slightly bigger than D. And for simplicity, we assume what is at least as big as 2. Well, we want to create large lower bounds. So if you can create large lower bounds for log, then you can, of course, create for log function. F d of I, say it's a log function. Maybe d minus 1 of I. round it up to natural number. And then I claim what? I claim R S plus 1 K plus sum over 3 to the I smaller than S. Here plug in function FB. Here plug in power of 3s, K plus S plus 3. This is big as 8. I function. Index omega S of K. K plus 1. So what does this mean? This means here is full power. It's a Ramsey function. Now the inputs are D, C, and M. This function is fixed. Here is also a sort of logarithm function or context. And if D, if S, K, and if this number is varying, S is varying, K is varying, then we get a function which is basically unbounded in epsilon 0. Now, to put it differently, let's assume that K is equal to S. Then I have here S. And I have here S. And then I have here S. This is H epsilon 0. This function is the diagonal function along all Hardy functions. So H epsilon 0 of S is H omega tau of height S. So you see these functions measure this function. So the Paris Harrington function gets astronomical values. That's part 1. Part 2 is now this is for fixed D. Next step is we make D depending on the arguments. So we get a result B H epsilon 0 of I is what? I take the binary log function. I iterated H epsilon 0 inverse of time times, apply to I, and then I take natural numbers. And then what? Then if I take this Paris Harrington function R, dimension S plus 1, here I have S plus sum 3 to the I smaller than S. Here I function H epsilon 0. Here I have 3S of 3S plus 5. So what does it mean? A tower of 3s of height S, and on top I have 3S plus 5. This is A omega S of S plus 1. So this is a very sharp result, because afterwards I will show if we replace this epsilon 0 by a fixed alpha, smaller than epsilon 0, then the Ramsey function for H alpha will be bounded by a fixed H beta, where beta is smaller than epsilon 0. So if I here take epsilon 0, the Ramsey function goes quickly. So it's still on this side. And when I replace this epsilon 0 by a fixed alpha, then I come to this side. So now we prove this. And the question is, how is it possible to prove this? But the only thing what we need is this one. And actually we even don't need a precise definition. We only need the lemma. So everything follows from the existence of the specific master partition. But this needs preparation. So recall the definition of the Hardy functions. So the Hardy functions were defined as follows: h0 of x was x, h alpha plus 1 of x was h alpha of x plus 1, and h lambda of x was h lambda x of x plus 1. Then remainder is h omega to the omega was already put as the Ackermann function. And you can imagine if you have omega to the omega to the omega, then you dominate all Ackermannian functions with n variable. But there is no bound on these towers, so you get enormous speed. And but there's something more, namely, we have also seen that these functions measure the length of descending sequences of ordinals, and that's used. So I will recall some sort of. So I prove first A and B comes basically as a one-liner from the proof of A. Although this result is much stronger than this one, but if you prove A in sufficiently general version, B comes by itself. We will see. So what are we going to do? Of course, we have to be very careful. One small mistake and everything is lost. Depending on where you make the mistake. So I somehow start with where do I start? Yeah, maybe I start here with alpha 0, which has the form omega sk. So I start somewhere in the universe, I fix some big number. No, the number is not completely random. It has somehow to do with the number which showed up over here. Anyway. So I start with the order big enough. Then alpha I plus 1 is I take alpha I and I step down in the fundamental sequences. So I have here I minus s plus 1. So if this number is smaller than 0, I just take 0, and otherwise I take the numbers over here. And n is the least number I, such that alpha I is 9. Okay, now we get a descending sequence of ordinals, and we have a number n. And we will show that n is a lower bound for this number. That's fine, then we are done. Second case is what has n to do with the Hardy functions? Well, that's easy. First thing is n is bound by h omega s k a plus 1. But how does this go? Well, we start with alpha 0. first we cut off the n, and some of the fundamental sequence start drawing. So for I big enough, we have what? H alpha I minus S minus 1. This why I have this definition of the Hardy functions. So I always go down this fundamental sequence and makes this inner argument better. So here I have H alpha I plus 1. And here I plus 1 minus F minus 1. Okay, and then H omega sk of k plus 1. It's the same as H alpha n of k plus 1. K plus 1 is the same as n minus S minus 1. Now I use these equalities. So we get here H alpha, or replace small n by capital N. N minus S minus 1. Now, what was the function of capital N? Capital N is the first I where alpha I is 0. So alpha n is 0. The Hardy function at level 0 just gives the argument. So this is n minus S minus 1. I'm showing is this one, namely this is bounded by n. But that's fine, because what I want to show is, I want to show basically that this number is a lower bound for this number. What I'm showing is that the number n is lower bound for this number, and n clearly this number. Okay. Now we have to figure out what do we know about the alpha i's. They are descending sequence of ordinals of a large length, but the point is, you see here, you have control how alpha I plus 1 comes from alpha I, namely by stepping down in the fundamental sequence in a linear way. Basically, when you're at time I, you step down at argument I. So you do not go too quickly. So what this basically means that the complexity, the maximal coefficient of alpha I is basically proportional to I. Okay, that is what we now write out. So yeah, this is the work. Maybe I continue over here. So what do we have? For I let's into n, we have for I smaller than n, we have alpha I is bigger than alpha I plus 1. Okay, that's good. So in some sense, what we want, what our plan is to move the alpha i's in the corresponding sequence of beta i's. Then we want to apply our master coloring. So we induce the coloring on S tuples of natural numbers into master coloring of the corresponding orders. The question?
Yeah, so like for I values less than S plus 1, alpha I and alpha I plus 1 are equal, right?
No.
Oh no, because we set down as 0. Yeah.
Alpha I of 0 is always smaller than alpha I.
Yeah.
And the point is, what we do in the beginning, we just subtract ones. So to say, only to, after n times subtracting 1, we have this situation. So this n is basically some sort of padding, so to say. You do nothing, basically you wait until your index I is big enough so that the following inequalities are going to apply. So we have this observation, that's fine. And now the fixed number kappa is s plus n plus p, which is the same as 2s plus k plus k. Now comes plane. Namely, if I is less than or equal to n, then the maximum coefficient of alpha I plus s smaller than kappa. So this is basically arranged by starting with here given n big enough. So here is the asymptotics of the maximum coefficient. It does not depend on I. And B, if I is big enough, then the maximum coefficient of alpha I plus S is bound by I. That is what I basically said, namely that if you are going deeply into the sequence, it's basically the complexity of alpha I is bound by I. That's trivial verification. Whatever trivial means in this context. But just starting with the alpha I is not enough. The alpha I's are somehow the beginning of the story. And so what? So the proof. So easy, I can finish it already. So proof. If I is correct, then what? The maximum coefficient of alpha I. Basically, we cut off just once, so bounded by the maximum coefficient of the first one. So it's bounded plus S, bounded by the maximum coefficient of alpha 0 plus S. The maximum coefficient of alpha 0 is bounded by what? Maximum coefficient of this one is bounded by the maximum of k and n. Maximum of k and n plus s. And now we look what is the number kappa. Kappa is very bigger. So that's a trivial adjustment. You just choose kappa so that it's going to hold. It's A. B is also easy. So we do induction on I. The starting case is I is equal to n. So the maximum coefficient of alpha n plus s. Well, what is alpha n? Alpha n basically says we have cut off the n completely. So that's bounded by k plus s. Bounded by n. N is k plus s plus 2. And now induction step. Assume if the maximum coefficient of alpha I plus s is smaller than I. And then the maximum coefficient of alpha I is bounded by R and S. And the maximal coefficient of alpha I plus 1 is the maximal coefficient of alpha I minus S minus 1. Now I is so big that it's bigger than S minus 1, so it's the real difference. That's bounded by the maximal coefficient of alpha I. The maximum coefficient of alpha I. And the index over here. Okay. This number will fix this estimate. This number is also smaller than I minus S plus 1. So this means the maximum coefficient of alpha I plus 1 plus X is smaller than okay, that's fine. But there's something bad here. And what is bad here? In the master coloring, we bound here in the maximal coefficient. Now what we want to have is basically finally we want to squeeze with a log function. So what's needed is logarithm. So the alpha i's are not fulfilling what is asked for. Now what's going to happen is the following. We have here our sequence. But this has complexity linear in, so alpha I has complexity linear in I. Now we move this sequence into a new sequence. So that the maximum coefficient of beta I is bounded by the logarithm, iterated logarithm in I. How is this possible? Well, it's sort of like in physics, you go to a phase transition, then you have to do some sort of what's called renormalization. So you have to squeeze some of your stuff down, and that's not going to happen. Well, everything is just brute force combinatorics, but you have to keep this in mind, that you have to press down the complexities. And the complexities of the alphas are too large for our purpose. Well, in the meantime, I have to wipe out some stuff. So this one is involved. So we need a small lemma, namely what can we say about if alpha is smaller than omega sk, then the maximal coefficient omega sk plus alpha is bounded by the maximum taken over the maximal coefficient of alpha. But this holds for alpha smaller than this number. And the reason is, if you write down this Canton form, well, this is the new term to the left. The maximum coefficient here is k. And for the rest, I take the maximum coefficient of alpha, and the one is just some trivial matters, that the coefficients are showing up. Now that's part A and B. B is that if alpha is smaller than omega sk, it's equals 2, then it follows that the maximal coefficient of omega sk times alpha, bounded by the maximum coefficient of alpha k in 1. Now that's not obvious, right? So A is obvious because it's under normal form, we just have a new term, it's confused with k. Here it's somehow different. So it's important that alpha is smaller than number. So assume you write alpha as omega to the alpha 1 times m1 plus omega to the alpha n times m1. Now what is omega s a times alpha? It's the same as omega s k is omega, so omega s minus 1 k times alpha. So this is times omega to the alpha 1 times m1 plus omega to the omega s minus 1 k plus alpha n times mn times mn. So what is the maximum coefficient here? It's a maximum coefficient over here coming from the m's. The m's are showing up in alpha. Here the alpha i's are showing up in alpha. And you have this omega. Let me see, you can apply a because the exponents alpha I are smaller than omega s minus 1. So we are done. Cool. Yeah. So this is the preparation. Now comes the magic. We do this step. And how can we do this? Yeah. Let's say we define the number n prime enough for our purpose. Ps x plus n plus 3 and beta 0. So here's alpha 0. Beta 0 is what do I take here? Omega might be that I have to modify it. Okay, I put here 1. We will see what this makes. The I is beta I plus 1 times 4 I is equal to n prime. So what does this mean? We just cut off the numbers. What is ML? ML is a set of ordinals, completely random. Set of ordinals alpha smaller than omega s, let's say k minus 1. K, I know where is k minus 1. Let's see. The maximum coefficient of alpha is so what can we say here? We have a bound on how big these objects are. And the only thing what we know is the complexity is bounded by and the iteration function enumerates an L in increasing order. Now, if I becomes bigger than n prime, put I S. Take omega k s times alpha. Now it comes. Take here binary log b times iterated by Now what's going to happen here? Well, the basic idea is the following, namely the maximal coefficient of alpha I is basically bounded by I. The maximal coefficient of alpha log of I is bounded by log of I. The maximal coefficient of alpha log d times iterated is bounded by d times iterated by log of I. There's a problem. The alpha i's are strictly decreasing. The beta i's are weakly decreasing. That's a problem. Because our master coloring assumes strict descending sequences. But here you see how I smuggled in reduced complexities. Now I have to compensate for this situation. And what I do is, so now comes the trick. I take the innovation function of function ZML, and ML is log 2 d times iteration by 5, and then the integer function of. Now I take the ordinals in this set basically in decreasing order. So I take 2 power of 2's of height x minus 1. And here I take log 2 s d. So what is this? Well, the iteration function basically iterates in increasing order. Now, if I have an iteration function with decreasing indices, I get a descending sequence. Now, the trick is this part is weakly decreasing, and this is strictly decreasing. This guarantees basically that the beta i's will be strictly decreasing. Now, what can I say about the complexity? What can I say about the maximal coefficient showing up here? Well, the maximal coefficient is here bounded by log d. And here, the maximal coefficient is bounded by, you see here, this L. L is bounding the maximal coefficient of those elements in this set. So in total, the complexity of the beta i's is small. That's what I would say, this renormalization operator. You squeeze the descending sequence down into a new descending sequence of very low complexity. And that here's what is going to happen. And now we have to show that everything is well defined and something like this. But this is somehow the core definition for the whole proof. Now, of course, it's moment for the break. So there are two options. Either we do a break or just continue. Or maybe you can make a break right now. You can try to understand what's going on. But here it's going to happen. Now the beta i's are going down. Then I apply my master coloring to the beta i's, and then I squeeze out the result. And yeah.
Perhaps it's an option to like first and then.
Yeah, we can also continue, whatever you like. So then I just continue when there's no But sometimes people want to go to the restroom. You can do a break
Right
after.
after, yeah.
This,
Yeah.
yes, I finished the proof. And, but what you see here is also this sequence can be done for all indices I below in prime, because the sequence of alpha i's at length capital N, and then the sequence of beta I can be made as long as the sequence of alpha i's is. It's even a bit longer because here I use indices which are smaller than the indices of the alpha i's. That's important that we now get a sequence, sending sequence of length capital N. So this is so what do we have to show? We have to show something. Namely, first of all, we have to figure out how many elements are in the set M here. Because this number has to be smaller than the number of elements, because the enumeration function works on the cardinality of the set. And if you take plus infinity, the enumeration function already has enumerated all elements and then doesn't know what to do. We have to show that this number here is smaller than the cardinality of the set. Okay. And then we have to show that it's strictly decreasing. So first of all, beta I, it's well defined. That's not clear, right? It needs a proof. Now, what can we say about the number of elements in ML? Well, I think, at least I hope that I did it before. These sets in cardinality are bounded by, take my slogan hierarchy of index omega s k minus 1. And plug in here L. Yeah. So the G function was defined as follows. 0 of x was 0. The alpha plus 1 of x was 1 plus the alpha of x. And G lambda of x was G lambda x of x. Now, what was the point here? This function is magic in the sense that G omega, the alpha plus beta of x, is basically x plus 1. G alpha of x plus the beta of x when you give this Cantor-Norton force. The G function was this homomorphism of ordinals into natural numbers. The counting of sets was using following function. I used G0 of x of 0, G alpha plus 1 of x is 1 plus G alpha of x, and G lambda of x is 1 plus G lambda x. Now, what is the role of this function? Basically, one can show what the number of elements alpha is smaller than beta. Maximum coefficient of alpha is bounded by L, is bounded by this one, L plus 1. This is at least as big as G beta L. G beta of L is bigger than or G beta of L. Now, what is the upshot here? The upshot here is that this is basically energy has to be bigger than this one. This one is what? It's a function L and S times. And on top I have K minus 1. So by brute force combinatorics, however you do this, these sets ML basically have a sort of number of elements is iterated exponential in the number L, and the height of the exponential tower is given by the height of beta. Now I do some rough estimates, which are not so interesting. What's important is now L is log 2 of I. So this is at least as big as what? And now take a 2 to S minus 1. Of log 2. So what is the upshot? The upshot is this set ML contains at least as many elements as this number. And therefore, all these numbers are smaller than this number, so therefore the enumeration function is well defined. For all I, and all these arguments, this one, so all these arguments are, and here is even a strip bigger, so there's no discounting going to happen. And the reason why it's going to hold is, we do this estimate for I bigger than n prime. And n prime, here is a bit nuts. Okay, now next trick. Beta I plus 1 is decreasing. Why is this the case? Now, two cases. This function here is weakly decreasing. Now, if it happens that log 2 I is strictly smaller than log E2 I plus 1. Wrong. Questions?
Yeah, so in the definition of beta I, the arguments inside the enumeration function, that's the last term is a -1, right? Or
Minus I.
minus I.
Yeah.
So is that negative then? Negative.
No. S is much bigger than D. Or S at least as big as D.
Yeah, but it's not an
It's
exponent.
It's not in the exponent the I, it's later. It's first do the two.
Yeah, you're right.
Yeah, okay.
Okay, sorry. You're perfectly right. It's not in the exponent. So the point is, I want to have enough elements in my set. I need as many elements as they are here, which I just showed. And then if I subtract elements I, then if I becomes bigger, the index becomes smaller, and therefore get descent. Now I do this argument, why is beta I plus 1 smaller than beta I? Well, that's not difficult. So beta I plus 1 starts with omega ks times alpha, and here comes log 2 d I plus something which is smaller than omega ks. Now, so here is what? Is I plus 1. Right. Now, this number is smaller than this number. So alpha index this number is smaller than alpha index, stop. Yeah. Alpha index this number is bigger than alpha index this number. Now I move this stuff to a larger ordinal, multiply the left is omega ks. This means whatever is coming over here, comes some beta smaller than this will be smaller than omega ks times alpha log d of I. Right. So whatever is coming here, it doesn't matter. This number here is smaller than this number here. The alpha i's from a decreasing sequence, and now I make them bigger by multiplying this number from the left. And this multiplier is bigger than all elements in this set because they are bounded by this number. Okay, that's fine. And then you see this is less than equal to zeta I. So that's this situation. Now, in the other cases, so here we are done. And now assume that the log functions produce by constant value. What's going to happen? Well, let us consider this number with beta I. And what you see is that this number is the same as this number. So beta I and beta I plus I start with the same first terms. Now, now we have to look what is going on with the second terms. And this is rather tricky business because here I have n, L, but L is log d2 I plus 1, and here is m log d2 I. But by magic, those numbers are the same because we are in this case. And then we have here 2s minus 1, whatever. Log d of alpha 1 minus I plus 1. And here is the same number. But now minus right? So this term is the same as this term, but this one is bigger than this one. So this means the whole number here is smaller than the small number here. This means in the enumeration, this object here is enumeration function. In the enumeration, this number comes before this number. And that's the reason why beta I plus 1 is smaller than beta I. So now I calculated, and now I collect what we have. So I cut off this one. Yeah. Well, what can we say about the maximum coefficient of beta I for n minus n? So the maximum coefficient is basically given by this number, right? Because these numbers are bounding the maximum coefficients of elements of ML. And here is the bound which we have for the alpha i's. And we have seen already the lemma that the maximum coefficient when multiplied with this term from the left doesn't do much. So the maximum coefficient is bound by this. The beta i's smaller than sk plus 1. Why is this the case? Oh, this k plus 2. Well, small change here. But that doesn't matter that much. Okay, and for the rest, these numbers are small. And the alpha i's smaller than omega s a plus 1. And the beta i's are, what can we say about omega kx, omega sk times alpha I? That to be smaller than this number. So now the question is, why is this the case? The reason is that the following: omega s k is omega to the omega s minus 1 k. S was the least and the biggest 2. The alpha i's are bound by this number. Let's say alpha I is some cardinal form, omega alpha I 0 times m0 f here times omega to the alpha I0 times m0 plus omega alpha IL times ML. And I have to show that this is bounded by omega to the omega s minus 1 k plus 2. Now, when you multiply out, you get plus over here, you get omega power, omega s minus 1 k plus. And now what you see here is omega s minus 1 k plus 2 is closed in addition because it's all in omega power. And therefore, these numbers, these sums are smaller than that one. Aha. So now I have to readjust a bit because I now moved this k into k plus 2, but anyway, it doesn't matter that much. What we now do is we define function f. I now define a partition P, which has only short homogeneous sets. I define it on number n. That's one into, I have to replace k by k plus 1. But this doesn't matter. So this number is the cardinality of this. The whole number here is the number of the CK set. And f of s plus 1 tuple. I take Q, beta I0, beta IS, and here's S, and now here I have to take k plus 1. And I know that's slightly inaccurate, but it doesn't matter. You just have to place k by k plus 1. This is well defined because the beta i's form a descending sequence. Okay. So you see here, this is a partition working on s plus 1 tuples of natural numbers. And somehow I have to induce a Bayes partition. And the magic in the argument is we move everything into a situation on ordinals. It's going to happen here. We use our master partition. Now, what's happening when I have a homogeneous set here? Let H be of the form 0 to IL, with an increasing order. Let this be F homogeneous. If all the values on S plus 1 tuples are getting the same value under F, then the corresponding sets of betas is homogeneous for the master partition. Then 0 to beta IL is T S k plus 1 homogeneous. Now we are in this situation. K is in the meantime k plus 2. Okay, it doesn't matter. The length of the sequence is now L is the L is strictly bounded by the maximum coefficient of beta I0 plus the height of beta I0. Okay. Now, what can we say about the maximal coefficient of beta at 0? Two things. It could be somehow this trivial bound. So if I'm in the beginning, this number is basically bounded by n prime because n prime is bigger than this k. So this is bounded by the maximum taken over what? N prime. And here I have log d I0 plus the height of beta I0 is bounded by s plus 1. Okay. Now bounded by maximum over n prime. Now I make an estimate. I bound it by log d minus 1. Since I0 is if I0 is less than or equal to n prime, I use this bound. If I0 is starting becoming big, I use this bound. And then log d minus 1 is bigger than log d. Log d minus 1 also measurizes this s. So this is then the maximum taken over what? N prime and log d minus 1. And here I0 is minimum of h. So what does this mean? The homogeneous set is cardinality L plus 1. Yeah, less than equal to 2. This is bounded by this one. What do I have to show? I have to show that this here unit of 8 should be smaller than this one. Okay, so I make here a bit smaller. I'm making here n prime plus 1. That's fine. And here I have this estimate where I have a big number. I apply d times iterated logs to it. And if I only apply one log smaller, then I have here strictly less than. So I get this bound. So what does this mean? This means this partition F is a property that all F homogeneous sets have cardinality smaller than number. Maybe I did a 1 over here. This was basically n prime. And FD in the meantime became minus 1. Okay, that's not an issue. Then it is shown that this Paris Harrington number must be bigger than this number n over here. And we are done. So that's basically the proof. But you see how tricky the proof is. I squeeze down the ordinals as good as I can. And now comes the basic explanation why I was forced to change my master partition. And the argument is the following. I can do the same thing and using here the rank function. Right? The proof will work. The only problem is that this will break down. So the number of elements in the set with rank is bound by L. So I spoke to Philip Floodley in Paris, and he said this is bound by a double exponential function, which has a fixed complexity. And what is needed is I need to build up powers. Therefore, I need the maximum coefficient. And therefore, I had to go into the proof, figure out where can I modify it, and then it's going to work. Okay, now it's a moment for a break. If you lost track, doesn't matter. I will now do something else. Right? So the whole lecture is a collection of nice results, something like this. And so after the break, I will cover the bounds when I did not do the full proof. After the break, this was part A. I will just show how part B follows from part A, but that's easy. And then comes the provable part, so to say, it's also easy. And then I study Crossbill's theorem about finite trees. And when you have never seen the proof of Crossbill's theorem, it will be a beautiful one. It will be one which you will not forget, because it belongs to the most beautiful proofs which exist in mathematics. So, and it's just doing mathematics out of the blue. So it's like Ramsey, but it's even more famous than this one. Okay, but now it's 12 o'clock, so a break until 12:15, and okay. I will stop the recording for 15 minutes. Victor, now it's a 15 minutes break.
Okay. Thank you.
Yeah. Yeah. Victor, when you're through, are you back?
Yeah.
Okay. Please check whether the laptop is still okay.
Yeah, maybe a little to the left. Yes, perfect.
I see. Okay. Now, so we did this one. And now we want to make substitution basically. FD is this one. Well, then this is fine, right? Because he's already d minus 1. I was miscalculating. I want to replace f by a function h epsilon 0, which is log function h epsilon 0 inverse of I to I. There's some rounding involved. And how can this be done? The proof is basically we collect the proof from A, and we take that all numbers are the same, right? B, we put S equal to K equal to B. Okay. Then first of all, H omega S of S plus 1 it's what? H omega S omega of S. Because if I have fundamental sequence for this term, I plug in here S for omega. It's true. That's skeptical. Normally I have to put in S plus 1 here, right? Okay. Now, if you already small mistake, it doesn't matter. Now for this one, it's correct. Now this one is the same as H omega plus 1. And now H epsilon 0 of S minus 2 formed by this number. Because I jump into the fundamental sequence, and then I have to add a 1 here. Fundamental sequence for epsilon 0 is maybe omega S minus 2. Omega S minus 2 is bigger than this one. Okay, it's fine. Maybe I plug in here not S minus 1, but S minus 2. Anyway, these functions are still growing. Okay, now let function f be starting from n, from 0 in, s plus 1 into a plus 1 plus some over e to the r. That's smaller than s. S in the version A. N was maybe this number. N was a number. Let's get big places. No, N was a Paris Harrington number. No, N was a number. Was it the least I, such as the alpha i's were hitting 0, right? And in A, this N was bigger than this number. So this capital N bigger than this number, bigger than this. Now comes the trick. For this number N, and let D be the restriction in shorter domain. Now, if H is homogeneous for G, then what? Then H is homogeneous for F. So F plus 1 is smaller than the maximum taken over n prime, and log minus 1 of the minimum plus 1 maybe. Okay. So now the magic comes. we want to replace number by this one. How can this be done? Well, for numbers I and n, we have what? If you take functional inverse of this function, times 2i, well, h epsilon 0 is strictly growing, functional inverse is then also weakly growing. So we bounded by h epsilon 0 inverse of the number m. Which is s minus 2. What does this mean? This means h epsilon 0 of I is what? Log 2 h epsilon 0 inverse of I. So these numbers are bounded by these numbers. So this is bigger than log 2 minus 2. And therefore, then replace this one by h epsilon 0 inverse of h. So this magical argument is that this h epsilon 0 function grows to infinity, but very slowly, and in the beginning, so this goes, the beginning is bounded by s minus 2, and then I can do this estimate, and then I'm done, right? So it's basically the proof. But you have seen this argument somehow before, right? So first I prove phase transition for some function with a fixed parameter. And then I make this parameter dynamic, because in a certain range, this fixed parameter can be compared with a dynamic parameter. Okay. Now, finally, now comes something very simple. Let f alpha on epsilon 0. F alpha of I is binary log h alpha inverse of I. Then the remedy function for dimension n colors, vector function f alpha applied to n is bounded by h alpha of n plus 3. And here comes the tower of 2's of height, let's say n plus 3. So what we see here is basically this function is bounded by a fixed function h beta. So when you go from alpha to omega to the alpha, h omega to the alpha of n is bigger than this term. So you get an upper bound. Okay. So proof. This we use Ereshbadu classical paper, which I will not prove. That is somewhere in the literature. Gerardo basically showed some concrete bounds on Ramsey numbers. For standard Ramsey numbers, something like this. So the tau exponential of height t, then have d factorial, which is d times c times logarithm of c times m. So what is basically what we see here is basically the Ramsey function is bounded by a power function, basically given by the height, the dimension of the partitions, and the rest is somewhere hidden in the exponents. Okay, that is what we use. And then we show this one. So let n be this number. And if I do here a miscalculation, let's say, of course, this is too small, and I replace here 3 by 4, then it should work. What is then 2? N is bigger than 2, n plus 2. N times a alpha of n plus 2. Is this true? Question. I guess so. Right. And otherwise, if it's not true, then we make a 4 and this is 3. I call this number n. Now you can wonder why I'm choosing this strange term. Well, let f be an arbitrary partition. 0 n and n. I want to show that this has a large homogeneous set. Take now a new function, g. It will be the restriction of f to the domain h alpha n plus 3 and m to the n. So that's a shorter domain. This goes from the small domain. Okay. Now, by standard Ramsey, there exists a homogeneous set of what I'm saying is what? So what can we say about the canality here? The canality of this thing is at least as big as this number, because I'm going from here to this number plus this number. If I subtract this number, I'm ending up here. So now I want to use Gerardo for this number. So this number should be big enough for D. Find H homogeneous with canality of H at least as big as H alpha n plus 3. So this is a number which is rather big. And here we have towers of height d, is to n, but here is n plus 2. So all the stuff coming here is basically eaten up by n plus 2. Also, the number of colors is majorized, and m will be the canality for the homogeneous sets. Okay, and then we have what? take log H alpha inverse of the minimum of H. It's the minimum of H. Now we have to bound this. Now the trick here is this function is monotone in this term, but anti-monotone in this term. So when you want to make this bigger, I take here H alpha inverse of. Then comes the trick. I take the leftmost endpoint over here. It's alpha n plus 3. And here I take the rightmost endpoint, namely I take m. And m is even smaller than n. So what? Its log becomes n plus 3 of n plus 3 of H alpha n plus 3, which is H alpha n plus 3 bounded by the penalty of H. So the penalty of H is at least as big as this, and at least as big as this one. So total penalty H at least as big as the maximum taken over H alpha n plus 3 and H, what is it? F alpha. The minimum. And this F alpha minimum of H is bounded by this number. This number is bounded by this number. This number is bounded by this number. So the result is shown. And you see these versions follow trivial by trivially if you have the bound from finite combinatorics. And the philosophy is the following. So this works with fixed D. Fixed D can, so if you do this one, well, it works basically when you can somehow invert this function. When your phase transition function is basically the inverse function of finite combinatorics, you're fine. But the inverse function is basically a sort of log star function. So for log star, you get low complexities. But what we learned over here is when you have a fixed log function, and D is varying, then you definitely don't get the function inverse. And therefore, this argument, what I'm using here, is no longer applicable, and this is an indication that you get large complexities. Yeah.
It's appears to me where we use adverse analysis of
the point is this interval, this one, has so many, at least so many elements. And now the Ramsey number will be smaller than this number. So I want to have a Ramsey number for n, dimension n, and number of colors n. Number m is this one. And this Ramsey number, so R, n, n, and alpha n plus 3 will be bounded by this number. Right, and if you have a partition of a set with so many elements, you get your homogeneous set, at least as many elements as here. Now here we have a bigger number. So when you partition the bigger set is continuity here, it has even more elements than the Ramsey number. So it's guaranteed by Ramsey that you find a homogeneous set of continuity given here. But your question is sensible. Maybe I didn't explain it too well. And now it's a bit of remaining time. 5 minutes. It doesn't make sense to start right now. So the next chapter is a complete new chapter. It's about finite trees, and I will cover Kruskal's theorem. It has a bit of a flavor of Ramsey's stuff. So basically what it says is for every infinite sequence finite trees, there exist two moments in time such that the first tree can be in an appropriate way homomorphically be embedded into the second tree. And you will normally not be able to prove this because it has a logical strength and you need a comprehension where you need an unbounded set quantifier. Normally in mathematics you don't need this. But this is a complex statement, but it has a very simple formulation. And then we use a famous argument by Nash-Williams, famous minimal bad sequence argument to show this one. And the next thing is we apply compactness. And compactness is giving for K there is an M such that for all finite sequences, finite trees, if for all I equal to M, the number of nodes in I is bounded by K plus I, then this is either to M such that I available in J. It's a famous reformulation. This is an infinite statement speaking about infinite sequences of finite objects. This is a statement speaking about only about numbers. This is also complex. You will not be able to show this. So what we do is we take the infinite version, apply a Königs lemma, and we get this one. But this is a trick to say it's not a cheap argument. And then we do the phase transition in terms of we replace here the density function by the function f. And then we will learn about this funny constant, which is related to Kruskal's theorem. And the funny constant is not known to be transcendental or rational. Just we have an explicit description. You can calculate with a computer 100 digits, but the true nature of this constant is unknown. Normally, it's an indication that it's transcendental, but we don't know. Okay, that is going to happen next time. Now, regarding the presentations, you have to agree on some moment. And how often do we have still lectures? So today is 2. Then next time it's
there are 2 weeks left.
2 weeks left. So it could be that I do another lecture online just to compensate because I was 2 weeks away. I was sick for 1 week. And 1 week I did only half a lecture, right? I was this problems could we see. So I will at least add another half lecture on the internet, and maybe another full lecture, but just to compensate for this. And so with the presentations, what about last Friday in the afternoon?
The last Friday, so
yes, in 2 weeks.
For me,
We just
Afternoon, so not
afternoon after lunch. So
some extra class.
some extra class just for doing the. We also did not have the exercise classes, so this will compensate for the missing exercise class. Well, it's somehow a mixture of project with the presentations. It compensates for this. And I also said that we do a written exam, right? So for this, you can also make first check among each other which is suitable for you. Then I have to check with the other class. It's not the same date, right? And yeah, then we find some solution. And what I also will do is I have here my handwritten notes. Every now and then I will slowly move them into PDF, and I will put it on Ufora.
And the exam will be like exercises, like the
So it will be two parts. One is exercises. So what was the agreement? Project, 5 points. Presentation, 5 points. And then I do the exam. Exercises, 5 points. And some theory questions, also 5 points. But what I'm checking is basically ideas. So you can imagine that this type of calculation you cannot learn by heart. Yeah. Let me say the following. I didn't decide yet. So for the theory part, I have two options. Either you use the notes, then I can ask more detailed questions because you have the notes, or I do a closed book and then I do some general questions. But I didn't decide yet. So it's all a bit what you like now. Yeah. Okay, that's it. But you see, when you have this, okay, then the chance of failing is basically equal to 0. Don't worry too much. And there's one exercise in the project which is difficult, you might have recognized, but that's a voluntary, so to say. It's really testing a bit of research, but if it doesn't work out. But if you want to do something more challenging, this is good. And once you did that one, I have lots of more interesting questions related to this, but don't worry too much about this. Okay, so much for today. Yeah, I'll stop the recording.
And for the written exam, will there later come in for like a more
Yes, I will.